good. So this is just total aside. Just thought of. So we talked about Hooke's law, which says, you have a spring. I don't know if you can see. You must have seen one of these before in your lives. And says that the force is proportional to the distance you pull. But of course, Hooke's law is one weird thing. Someone decided that in physics a law is something which doesn't sound right. A law seems like, well, it's the law. You can't get around it, but it's not. A law is just something that you observationally observe about things. It doesn't have to always be true. And in the case of a spring, you can only do this once here. While it may obey Hooke's law within certain parameters, if you exceed those parameters, then it no longer obeys Hooke's law. So, okay. That has nothing to do with this course, but Angie's not here, right? That's the last thing. So there will be a quiz next Tuesday. That'll be the last quiz.
No.
Okay, we'll have another one then.
I'm just kidding.
Just for you.
Take home.
T6 was right. Students want to pay a lot of money to come someplace and then be disappointed. So it'll be on differential equations. I guess we had a homework. Do we have a homework assignment? I guess we did. Are there any questions about that?
Is that due next week though?
It's whenever.
Or on the phone?
You just got to get it in by the final. Get any homework in. I mean, if you want to see it, get it in now. I won't be able to get it back to you if you give it to me at the final, but I'll look at it. That extra credit homework thing, that's not due till the final, certainly. And if you want to know how you did on it, let me know. Okay. No questions on the homework? Yes.
Can you do number 8? It's page 498.
What can you say about the graph of a solution of the equation y prime equals xy cubed when x is close to 0? Well, if x is close to 0, then x times y cubed is close to 0. Right? So the derivative is close to 0. So I don't know what it's doing. We have some solution. That like kind of gets large because of y cubed. As it comes in, it's going to have to get to 0 at 0, right? What if x is very large? What if x is large? Well, then your slope gets close to vertical, right? I think that's what they're looking for. Okay, did I give you A, B, C, and D? Did I just say A?
Just A and B.
Oh, just A and B, okay.
What page are we on?
498.
498?
Just A.
Am I on the right page?
498.
Okay, part B, actually, that's really the part I wanted you to do. I mean, you know, sign day, but interesting question. Verify that all members of the family y equals c minus x squared to the minus 1/2 are solutions of that equation. All right, that's something we did on the board, at least one problem last week, so let's write this all down. So the differential equation is y prime equals xy cubed, and they want to know that y equals, I'm just going to mention this again because I don't want confusion. In these equations, implicitly, this is a function of x. I could write it as y prime of x equals y of x cubed, but, you know, just to save on expo dry erase markers, we're just going to assume you know that. And we want to know that c minus x squared to the minus 1/2 is a solution. And when they say all members, what they mean is for all c. So we have to do two things here. We have to find out what y prime is. Okay. So y prime is going to be c minus x squared minus 1/2 minus 1/2 to the minus 3/2, right? Chain rule wants me to multiply it by minus 2x. So my minuses here cancel. Yeah, my 2's cancel. So I just end up with x times c minus x squared to the minus 3x. Okay, that's the left side here. So we want to see that's equal to the right side. Well, this looks good. There's an x, huh? So x times y, which is c minus x squared to the minus 1/2 cubed. Well, that's just x times c minus x squared to the minus 3/2. So they match. So that's going to work. Verifying a differential equation, that was the point. Last minute attendance. Okay, so one. Okay. Any other questions on the homework?
I was wondering for assignment 17, is it 7.3 instead of 7.2, or because the page numbers don't?
Yeah, I have been delinquent in my numbering.
It's 7.3, right?
Number 17. I haven't assigned that yet.
Oh, okay. I thought that was the one due for. Okay, never mind.
611. Okay. I will assign it today, but
Okay.
it's not due. The optional thing above it that says 611, like I said, that's not 611 anymore. That's just before the, handed in before or at the final. Don't be working at it during the final, please. Work on the final. Okay, any other questions on this homework?
Can you also do part A for number 3?
Part A for number 3. It says for what values of r does the function y equals e to the rx? By the way, this problem we're gonna do a little more with something that looks just like this today. So it's good. This. Y double prime plus y prime plus y equals 0. So what they're saying is assume this is a solution and see if there's some values of r that make this true. So we need to find y prime, that's r e to the x. Y double prime, that's going to be r squared e to the x, and we plug in. So 2r squared e to the x plus r e to the x plus e of rx. Rx, e to the rx. We can multiply through here by e to the minus rx because that can't be 0. We get 2r squared plus r plus 1 equals 0. Now we want to know if there's an r for which this is true. Well, this is just a quadratic equation with r instead of x. So we could try and factor it, or we could just use the quadratic formula. Negative r plus or minus the square root of r squared minus 8. I'm sorry, what am I doing? I'm brain dead. Negative 1 plus or minus the square root of 1 minus. Did I miss something?
Yeah, it's the initial equation is actually minus y. So it's y prime minus y. That's what it says in the book.
Minus y?
Yeah.
Oh, thank you. That helps a lot, doesn't it? So minus 8 over 4, which is negative 1 plus or minus 3 over 4. So minus would be minus 1, and plus would be 1/2. So those are the values. This is r. So we know that y equals e to the minus x, and y equals e to the x over 2 are solutions for that. Had to change something?
No, I was looking to see if
Anything else? Anything else from homework or anything else? Okay. So, tell me if I can erase this stuff now. Okay. Silence is a yes. It's too bad I can't keep this. Okay, so today, in our ongoing adventure with differential equations, we're going to learn a new and fairly straightforward technique called separation of variables. Unlike other areas in math where you have a set of problems and you just brute force, you go at them and you solve them all. Differential equations, there are all sorts of different techniques for different equations that people have come up with. There's no general solution, but this strategy works in some cases. In particular, if we have an equation of the form dy dx, derivative is equal to some function of x times some other function of y. That's where the separation comes in. The x and the y's are a product, so they're separable. The way we go about this, well, we're going to put the x's and the y's on the opposite sides of the equation. And this is 1 over, this is a multiplication, 1 over f of y equals g of x. And then we do something that is kind of a hand wave. I think I talked to you like at the very beginning about the idea that sometimes we do things notationally that aren't really correct, but they work. And that's what we do here. We say this is 1 over f of y dy equals g of x dx. This doesn't really make any sense. You can't take a derivative and break it up into the dy and the dx. But we'll show that this is valid in a second. But and then, having separated the x's and the y's, we integrate both sides. So what does this buy us? Well, over here, assuming we can evaluate this integral, we have some function of y, and over here we have some function of x, and we therefore get an implicit solution to the differential equation. That is, we don't necessarily have y in terms of x, but we have some expression where if you had a function and it fulfilled that requirement, this implicit requirement, it would be a solution. If we're even more fortunate and we can take the result of this and put y in terms of x, then we will have an explicit solution, and we've solved it. So we're gonna take a look at some examples of this. This is a little vague right now. It'll make more sense in a second, but I think it's worth just taking a second here. Now let's look at this expression. Let's see if we can do something legitimately to show that this is actually correct. And specifically what we do. Hello. Specifically, we're going to take each side of this equation and we're going to find the derivative with respect to x. So we have 1 over f of y dy equal to g of x dx. Well, this should be pretty obvious and straightforward by now. The fundamental theorem of calculus tells us that this is just g of x. Here, we don't have f of y in terms of x, right? But we can still apply the fundamental theorem. This becomes f of y times the derivative of y with respect to x. And now multiplying through by f of y, you see that dy dx equals d of x, f of x. That's f of y, excuse me. That's what we said. You know, we said these were equivalent. We've shown that this is equivalent to this. And so that trick, that hand-waving trick where we separate the dx and dy works. It just isn't, they aren't valid statements, but it's a valid way to solve the problem. Okay, let's take an example. So we can put some meat on this. Let's say dy dx equals x squared over y squared. So using this method, we have y squared dy equals x squared dx. And we integrate both sides. And we get y cubed over 3 equals, we only need one constant here, there's a constant involved, x cubed over 3 plus some constant. And lo and behold, we can solve for y here. We can say y cubed equals x cubed plus 3c. It's just another constant, right? Call it d. And now we can find the cubed root of y, and we get that the general solution is the cubed root of x cubed plus some arbitrary constant. We might have an initial condition problem. We might say, know that y of 0 equals 1. So instead of a whole family, we can get a specific solution. So y of 0 equals 1, it means 1 equals the cubed root of 1 plus d. And that, of course, implies that d equals 0. Okay, any questions about this? This is an example of using separation of variables to solve a differential equation. And the result is an explicit solution. We have y explicitly in terms of x. Questions? All right. Let's take a look at another example that's not going to be as nice. Let's say dy dx is equal to 6x squared over 2y plus the cosine of y. Okay, do our little trick here, separating the y's and the x's. And we integrate. And what do we get here?
Did you mean dy?
Oh, thank you. I think I even wrote dy and I overshot in my head. Okay, so integrating this by y, what do I get here? I get y squared plus sine of y equals 2x cubed plus some constant. All right, now you see the problem here. There's no way for me to express y in terms of x. But I know that any y that fulfills this requirement will be a solution to this equation. This might be particularly useful if you're doing some kind of numerical approximation. Right? Instead of using Euler's method, you can use this expression instead. Yes?
Why is there no C on the y side?
I'm sorry, why is there no C on the what?
On the y side when you integrate the y?
Well, let's say, that's a good question, right? Let's just put a C on this side and we'll put another C on this side. They're different C's, right? So I could then subtract this C from both sides. Now remember, these are some kind of arbitrary constant. We don't know what they are. We need an initial condition to remove them. So here you can see that whatever, if we picked a separate constant, now it's just one number. So we really can we can just treat this as a single constant. I did the same kind of thing here, where what's this? This is really 3C. It doesn't matter whether I call it 3C or D, since it's arbitrary. So it's a good question, though. Okay. Any questions so far? All right, we're going to do one last example. Let's say we set dy dx equal to x squared y. So again, we want to separate these two. We get 1 over y equals x squared dx. And we're going to integrate both sides. So here we have the natural log of the absolute value of y. Here we have x cubed over 3 plus a constant. And again, we want to have y in terms of x explicitly. So we're going to raise both sides of this equation to the e power. I guess I need more room here. And it helps to know that e to the natural log of y is just going to be, well, the absolute value of y is going to be the absolute value of y. E to the x cubed over 3 plus c is going to be e to the x cubed over 3 times e to the c. Well, this is not an arbitrary constant, but this is, so this is just d. And because this is the absolute value here, what we really have is y can be plus or minus e to the x cubed to 3. let's say we have, in this case, initial conditions that this one's broken now too. Sad. Okay, initial conditions. Oh, that's not what I want to do. I don't want to do initial conditions. I guess what I want to point out is that D could be 0, right? That is, y is equal to 0. And if you plug this back in here, you see the derivative of y is 0, and x squared times 0 is 0. So that would also be a valid solution to this. Maybe a less interesting one. So I guess we can say y is some constant x cubed over 3, where a is any real number. It could be 0, positive, or negative. Okay, that's separation of variables. We're going to do a little practice. So take a stab at these. Is anyone too cold in here? Okay, I'm going to open the door then. If it gets too hot, let me know. Close the door. Terrible teacher. I make mistakes. Okay, the chapter on separation of variables is 7.3. And did I screw up the homework assignments?
Yes.
Oh. Were you guys like checking up on my website this weekend? You found? Boy, you must have had a hard time doing something we hadn't gone over. I apologize. I'm sorry. Tough week, can I say? But no one will be docked in any grade-oriented way for having made that mistake. Did anybody freak out? No, good. Everyone familiar with the set of novels, The Hitchhiker's Guide to the Galaxy? Hitchhiker's Guide to the Galaxy is this little device like a cell phone, like a smartphone. Got all the information anyone needs traveling around the universe. but when you turn it on, it always says, don't panic. You should remember that. Whenever you're traveling around the universe, you go to my website, don't panic. Did I not give it to you? Oh, no, that's not what we're working on yet.
You didn't give me whatever worksheet.
I didn't give you a worksheet?
Nope.
Oh, sorry. My apologies. No, I don't have one. It might be. No.
I have an extra.
Hmm?
You can have mine. It's already from
Oh, you already did it. Oh, okay. Well, he's got one. You can keep it.
think so. Yes.
keep me busy. Could be good. Okay, everyone had a chance to get to at least number 3. Okay. Before we go over these, I realize I may have given you some bad information on some terminology. And the sad part is I'm still not sure. But let's see. So when we're classifying differential equations, there are ordinary, there are partial. The ordinary just have one variable, like x, and partial could have 2 or more. I didn't get that wrong. A linear differential equation is one where the function, I'm going to use some funny notation here. This means derivative n times, right? Where the derivative 0 times is just the function. But a linear function would be just one where the sum of these is a constant, these are multiplied by a constant. That would be a linear. I don't think I told you that wrong either. But then there's this issue of order and degree. And I think order refers to the highest derivative. I think I said that's what degree was, but I think it's the order. So first order, second order, third order. First order we just have derivative. The second order would have second derivative. But I think degree has to do with the, you look at the terms. So for example, in problem 1, y dx equals xy squared. I think this is actually like a third degree equation because you've got x and y twice. So a linear would just be a first degree equation of any order. I think I got that right. When you take the differential equations class, you can find out if I'm in error about that. Just be a little careful about those terms, order and degree. Here, the separable differential equations are definitely nonlinear, right? X times y squared, that's definitely nonlinear. And anything with an exponent variable is not going to be. So. Okay, would anyone like to try number 1 on the board? Okay. mechanics are very good. There's something missing.
Plus C?
There's something missing.
Is it the plus C?
Pardon?
The plus C? Plus C.
Plus C, yeah. You also have to see where the plus C, well, no, wait, be careful. There's a plus C when you integrate, right? What happens to that C?
But it's like still a constant. So it's still a constant. It's like still.
It's, okay, let's just,
Yeah, I'll just read it this part.
okay,
So
erase that, and a C. See, now when you multiply through by y, you get C times y, right? I don't know if that's what you want to do. Yeah, okay, that's fine, yeah, good. That works. Yeah, but you don't really want to separate the y, do you?
okay. Should I just leave it in terms of this?
I want a y equals. What is y equals?
So this is like
No, that's not right.
well, I can solve it in terms of.
No, I mean, you can't.
You didn't distribute the y.
Yeah. Well, you don't. She doesn't want to, but. And don't panic.
Oh wait, I just.
Okay, that's pretty good. I mean, you could play around with that too, but that's fine. That's the correct answer. Okay, very good, thank you. Would someone like to try number 2? Derivative of y with respect to x is x e to the minus y. Sure, give it a try. Remember, you got to be brave up there, you know? Doesn't matter. Yeah, just see if that works. Yeah. You could have a whole new board if you want. I'd rather have the space. Just push it up. You get your own private board. Pretty good to me. I don't know why, I'm just thinking.
But shouldn't that be absolute value?
Is it an absolute value?
Because if C was a large enough negative number, then that would be negative.
Well, okay, so there's, I mean, there's a family of solutions here, but that doesn't mean for every C this is valid, right? But it also, I mean, it doesn't mean this is true for all x, right? So, for example, if C is like minus 100, right? So there'll be x's for which this is undefined, so the domain will get restricted. There's a whole area of differential equations we're not going to deal with here, which is when you apply them to some physical situation, sometimes you get some areas the function doesn't work, like here, like you get a negative log. And resolving that is kind of a science question, not a, there's math involved. Okay, would someone like to try number 3? Wait, he raised his hand. Do you guys want to fight it out? Want to work together?
Okay,
I'll tell you what, you do the first part, you find your family, and you find the explicit solution. How about that?
Okay.
You have teamwork here. Okay, very nice. Okay, do you want to do part 2?
I'm just going to write this up.
Well, is it plus or minus?
It's minus.
It's just minus, right? Right. Because otherwise you can't get -1 at 0.
Yeah.
Yeah. Okay, very good. All right. Would any brave person want to try number 4? Really brave person? You want to try it? Okay. I'm going to help you out a little here. I'm going to erase the board. You might need a little more room. integration by parts, right? Remember how to do that? Or do you need a shout out? Do you need somebody to help you with that? Somebody want to help out with? Okay, this is an integration by parts. It's pretty straightforward.
Yeah, you.
And I'm not just talking to you, Floppy. You must know how to do this for the final. Okay. Integration by parts. Okay, that's good.
Completely observe how.
So here we have another implicit solution, right? It's not. There's no way to solve for x in terms of y, but we do know that any y that fulfills this requirement would be a solution. And now there's a constant. Daniel, thank you. I'd actually like to know if somebody would like to try the last part. Someone like to...
I like to think of it as exponentially raising those x by.
Yeah, that's not going to work. No. This is an example where you don't get an explicit solution. This is an implicit. Everyone remember when back when we were doing differentiation in another lifetime, we had something we called implicit differentiation, where you don't have y in terms of x, but you can still find the solution. All right, so what I want to see, though, is how do we apply this to find c, since we know that y of 0 equals 1, right? Well, on the left side we have, remember this is y of x plus log absolute value of x equals what we have up here. So y of 0 is 1, so that means 1
I figured it out.
plus, oh, too late.
Oh, yeah.
What's the log of 1? Right? Equals, we plug in 0 here, what do we get? 0 plus c, right? And this is 0, so we just have 1 equals c. So that gives us our solution, our specific solution, which is just replace this with a 1. Okay, why doesn't everybody take a break? Come back 10 minutes or so. There's a part of the homework is doing this. So I think actually all of the homework is just doing this. All right. Guys, you're going to keep me busy. Sorry. It's okay. It's my job. Remember what?
Define y plus
Look on the back.
yi plus 1 in terms of delta x. And y I and yi. You don't even need to
Don't
calculate
expect me to know everything.
X,
let's see,
This is one you can send it in.
assignments. 514. Well, that's homework for, this is homework for Thursday. Oh,
next X would be
okay. So,
you already got
you know your English is excellent. You know what that
Yeah.
means. This is that project.
Yeah, I thought.
That was the homework I assigned.
Okay, I thought that was just like a separate project.
It is. It's.
Yeah, I didn't know that was like the place of the second.
Oh, I see. No, I didn't give any other homework. If you, that's due.
But this is actually 7.2, not 7.
Oh, it's not. Oh, ooh.
Yeah, because you wrote 7.
Oh, okay. Yes. Okay. So let me fix that.
Yeah, that's all the finished class.
So, okay, I apologize, but again, I didn't tell you to go ahead and do the assignment for today, right? I have to be careful what I put up. You have a question?
Yeah. So,
Can I fix the homework before I get yelled at again? I mean, we're on break, right? So I have a few minutes. You have a computer there? Anybody have a computer? Okay, re-show. Tell me if I got it right. It does say page. Wait a minute. It says page 514, right? So I got the right page number. I put the right page number. You didn't look at the page number?
I know, but then I didn't know that the homework
I didn't-
project was in place of the homework, so I thought that you just have the page.
I'm sorry.
down.
Yeah.
Terrible person. You actually like had to go do some math that you really didn't have to do.
It wasn't that long.
I would hope not. Okay, okay, what's the question?
so on the right side, you said 0 plus C.
Yeah.
So you're
I
saying
left a really good
that,
back in my car and I didn't.
that the whole thing negative x cosine x plus sine x is equal to 0.
Okay, so we're trying to use, okay, this is the general solution, right?
Correct.
So we know this, but we don't know, that should tell us what C is, right? So we plug this in, here we get
It's
0
in my car, but I'm supposed to go.
plus, I'm sorry, 1 plus log of
Huh?
1
Some places take it.
equals
Yeah, I asked her, she
0
was like, yeah, there's some places
plus
that take
0
it. I think they prefer like
plus C.
non-diet.
So negative x cosine x.
Well, you plug in 0 for x.
Oh, okay, yeah, I see.
So 0 times 1, negative 0 times 1 is 0. Sine of 0 is 0.
Got it.
C, so that's where you get C. You have a question, Bruno?
Yeah, I actually do that. Like I put it in like really like
Sorry.
and then like I see on this side.
The hair is a little volume.
I'm confused. You wanted to see this, and you're giving me this. That's it? Okay, all right. Okay.
Like, if I find her up, because.
All right, I'm going to take a
Wait, do you do anything?
quick trip,
But
and I'll
it's
we'll
kind of
start
sad
in
because I
another
can't do it
couple
in
minutes.
Differential, it's way too short. I can't like grade it anymore. Like, I did, I tried, but it like ended up being super short.
Is it later?
Huh?
Is it later?
No, it's just nice. Like, just.
No, but it's later, it gets a lot shorter.
Some huge
Well, I rate it.
Yeah.
Like, I rate it once in a
That's why I
while.
was trying to go.
The one
Oh, you wait.
Yeah.
was from my macro.
But now that, like, when my hair was long, I just felt hella heavy. So, like, yeah, my hair was super flat.
Same here, yeah.
I cut it, it feels fluffy now.
Honestly, I did that close to 6 months.
Yeah.
That's like, oh my god, so I did it out, and there's like, this much hair on it.
He
But it's
got
still
my,
the same, it just stayed tied up, it feels so much harder.
Yeah, I know.
My hair
Yeah,
was
it's like,
super-
really
Like, I
nice.
stopped. I was like,
If you go
Wait,
for
where'd you
some knocking,
it was just like.
so you actually do have to stay around.
well,
This
it's
is
sort of
cute.
built.
Yeah.
Oh
I was
wow.
so scared to carry it. But like,
He's not as fast as anyone
Yeah.
else, but
And probably
if he
was
hits the
like-
ground, you have to be able to go around.
showering was super easy.
You have to
Like,
be a
you
certain
know, like,
amount of
like, I was
fast.
like in the bathroom, and they, I love
It's more about Miller.
I just.
Mr.
You get
You know, taking you
It was a lot more, yeah.
If you don't do that, you can get low and you're just gonna be able to hang up in the air.
Did you guys go to the
There's only a few guys in that. Alan was good in English and the slides I was
Yeah.
Oh, they
scary.
have the.
So he takes everyone else. You
Yeah.
just feel it.
Last summer I went in this.
And then also
I went a
Kevin.
few years ago, and it was like.
Kevin just made his fullback.
It was all what?
I suppose if you're going to do something, you do it clean all the
I don't
time.
mind. I
You
don't
hope you don't.
know. Yeah, I do.
They look at it.
I was just like, I don't know why you're staring quickly at
Try to
me.
balance.
Well, he's just probably
People
asking
foul
quickly.
either.
You were staring at me, so I'm staring at you. I
Just
feel like
take a
that's
look
just
at
what
this.
happened.
So you can foul. You can get nailed.
That's pretty cool, though.
Yeah.
I got to see that.
Body check,
Oh,
total
what did
amount
they say
of
like that last year?
Depends if they have the balls now. I'm not kidding.
Oh my gosh.
Because I really wanted to go.
Shoulders, like.
Didn't because I didn't want to pay more than $20.
Okay, is everyone here?
There's Matthew asked me.
2, 4, 6, 8, 10, 12, 13. Somebody's missing.
I couldn't do this, I have to take that SATs.
Who's taking the 3 martini lunch here?
What?
Actually, it's a 2 martini. 3 martini? I don't know. You know what that refers to? So like, you graduate, and you get some job at like some company, and you're not like, you're like a manager, and you hate your job.
Oh, that's
So
a
you
martini.
go out for a long lunch at a nice restaurant, and you have a couple martinis, and that's how you survive, you know, the pain and agony of your life.
That's a lot.
This is why you keep what's.
Or you become a professor.
You just keep the bottle in the little drawer.
Sorry?
Keep the plastic bottle in the little drawer whenever you just pull out real quick. Keep the bottle in the drawer. So whenever.
That's different. That's called drug abuse.
And you're sure that Ben's drinking martinis.
So why are you
Who's missing? Why can't I hear that?
Matthew. Oh my God.
Oh.
The other one, yeah.
Matthews.
We're so generic.
Matthew! All right, we'll just have to catch up. Before I really get into the next topic, I'm going to cover something. I just have this suspicion that your backgrounds in this might be varied. Some of you, this will be, just you know this already. So I want to look at something in general, and then we're going to go over it very quickly, but you should know most of it, and the parts you don't know, you might find interesting. And then you might not, I don't know. So if we look at this equation, a sub I, x to the I equals 0. Sum of this, right? Now, if this isn't really clear, let me just give you some examples. 3x equals 3x plus 4 equals 0. X squared minus 2x plus 5 equals 0. X cubed minus 1 equals 0. These are all polynomial equations, right? This is depending upon which one you look at. This is the feeling somebody's trying to get my attention. Sorry about that. Okay, nothing important. This is algebra 1. This is algebra 2. This might be algebra 2, might be calc. We know how to deal with these, right? So what about this general equation? Does anyone know anything about the general polynomial equation? For example,
I can write
how many roots, let's say I equals 0 to n. How many roots does that have? Do you remember?
up to the degree, I think.
It's not actually up to. It actually has that many roots.
Yeah, because I was thinking
Some
of
may be
irreducible.
duplicates. You might have duplicates.
No,
So-
I was thinking of irreducibles, but that's complex roots. Whoops.
Yeah, it'll have solutions in complex. In the complex field, it has n roots. I mean, you can have something like this. You can say, what are the 3 roots? Well, there's 0, 0, and 0. A little torture. But, okay, so I just want to talk a little bit more about this. So, everybody knows how to solve this, right? We just solve for x. How do we solve that in general?
Quadratic formula.
Quadratic formula. Not just this example, but how do we solve a quartic? How do we solve a degree 3 in general? Does anyone know?
No real idea.
Does anybody know? Anybody run across this?
I think it's kind of like a quadratic, but it's a lot longer.
That's exactly right. There's a formula.
Yeah, it's really long.
There's a formula. It was discovered in the 1700s, I believe. And it's kind of a neat, if you ever run across the story and how it's done, it's really kind of neat math, but we don't have time here. How about 4? Anyone know what happens when you get a 4th degree equation?
Hope that there's a common factor.
Well, obviously, yeah, anything, 100th degree, you might be able to factor it, but just in general. Turns out these two are very related. There is a formula. It's a little more complicated. Nobody expects you to remember these. You can look them up.
Is there a generalized formula for all of this? Because it really seems to be a pattern.
Yeah, you would have an exciting career in the 1700s as a mathematician.
Well, nowadays you
Because
still have
that's
it.
exactly what people thought. There ought to be. Now we go to this. We go to this. What happens then? Mathematicians spent a long time looking for a solution to this. And a huge branch of mathematics known as group theory. You know what a group is? That's okay. Group theory came out of it. And after, 40, 50 years, group theory was used to show that there is no general solution for this equation, or anything higher. So that's kind of the history of polynomial equations. It does have, we can prove that this has 5 roots, but we can't necessarily find them in some closed form. The roots may not even be like radicals, you know, in, well, okay. So that's important background. It's good to know. These things all have roots. Above 4, we can't necessarily find them. They could be complex, too. That's important to know. All right. So now I want to go back and deal with differential equations for a minute. Linear differential equations, and I want to look at a very general equation here. I want to look at the sum from I equals 0 to n, some constant, and y to some derivative of y or y itself. Again, y derivative 0, I'm defining as y, no derivative at all. And we set that equal to 0, and we want to know what the solution to that would be. So, how do we do this? Well, we take as an example some function in this form, e to the minus rx. See, maybe this can be a solution. So we're going to plug that in here, and we're going to find that this is going to be a to the I times r to the I e to the rx. That is, every time you, oh, did I say minus? I didn't mean that. Y prime is r e to the rx, y double prime is r squared e to the rx. Every time you differentiate this, you just add another r to the front. So we take this, and now we multiply both sides by e to the minus rx. And do this so clear. And we end up with this sum I equals 0 e to the I r to the I equals 0. Look at this carefully. You'll now know why I made all that big deal about solving a polynomial equation. Because this is exactly that. It's an nth degree polynomial in R. Right? And we know that we can solve this. Or we have hope that we can solve it. Because R, well, we'll have up to n roots. Not necessarily all unique. And then our solution will be y equals e to the, whichever one of these roots we happen to pick. I guess we'd say another letter here. Furthermore, as I suggested in a previous class, if you have a solution or solutions to a linear differential equation, then any linear combination of those solutions is itself a solution. I'm not going to show that today. I don't know if it will.
So
The solution...
ERI plus ERJ is also a solution? Or is that
Yeah, in fact, y equals some constant e to the rjx. I left out the x. Where these ri's are now solutions, one of these solutions to that polynomial equation. So every one of these will have that property that their sum is equal to 0. Okay, this is a little abstract. This is a very general kind of form. We should go through this and look at an example. Look at a few examples that are concrete. I could look at, say, like a1 y prime plus a2 y 0. There's no reason to have a
constant term, y0 term?
I don't know. Vocabulary is just kind of going with age here. A coefficient. Thank you.
Hey,
There's no reason to have a coefficient here. We can just multiply by 1 over a1 and it goes away. So we're just going to look at this equation. And following our strategy here, we're going to set y equals e to the rx, y prime equals r e to the rx. So r e to the rx plus a r to the e rx equals 0. We multiply through by e to the r minus x. We get r plus a equals 0. So r is just equal to minus a. I think we've seen this solution already. And so the solution to our equation is e to the minus ax. Or you can put a constant in front because any linear combination will also be a solution. All right, that was the easy one. Now we want to look at the fun one. This is a second order linear. So again, going through that same process, setting y equals e to the rx, y prime equal e r e to the rx, double prime equals r squared e to the rx. We get r squared e to the rx plus ar e to the rx plus b e to the rx equals 0. And again, eliminating the e to the rx factor, we get r squared plus ar plus b equals 0. Which we should all know how to solve by now. We're going to use the
Quadratic formula.
We're going to use the quadratic formula. So normally the a's and b's are in a different place, so let's be careful. So r equals here negative a plus or minus the square root of a squared minus 4b over 2. We want to think for a second. That's something real crucial here. A squared minus 4b. What did we call that in the quadratic formula? I mean, we usually see it b squared minus 4ac, but what do we call this? Does anyone know? Begins with a D. DI. Discriminant. Or is it A? I don't know, I'm not a good speller. Anyone remember what the discriminant is about?
How many solutions it has? 2, 1, or 0?
Okay, so that's true in algebra 1 or maybe 1A or 2A. But remember, there's always two solutions,
Yeah, complex.
right? So the discriminant tells you, is it, one duplicated root, two real roots, or imagined complex roots. Depends on whether a squared minus 4b is greater than 0, less than 0, or equal to 0. Well, let's look at equal to 0, because that's nice and easy. R equals negative a over 2. So our solution just becomes y equals e to the negative a over 2x. It's nice. That's this condition. Come back over here. Let's say a squared minus 4b is greater than 0. That means that I could have values r1, which are negative a plus the square root of a squared minus 4b over 2, and r2 equal negative a plus the square root of minus the square root of a squared minus 4b over 2. And my two solutions are with r1 and r2, so the general solution is just, we'll just say a1 e to the r1x plus a2 e to the r2x. Again, these being kind of arbitrary constants, but r1 and r2 are fixed by what a and b is. All right, so now we've gotten two of the three conditions. Now we want to look at the third one. So here we have r1 equal to negative a plus I times 4b minus a squared. And as I just reversed the order to make this positive over 2. And we have r2 equals negative a minus I times the square root of 4b minus a squared over 2. So what am I going to do with that? Well, these values are a little unwieldy. Let me just kind of say r is a complex number, so let's call it r plus is, and r2 equals r minus is, where I, of course, is square root of negative 1. So that would give us y equals e to the r plus is x, and some constant, plus another constant, E times R minus IS x. Well, there's something funny going on here. We're raising, we can rewrite this as e to the r, e to the is, plus a2, e to the r, e to the minus is. Gotta get those x's in there. Does anyone know anything about what happens when you raise e to a power which is multiplied by I?
You're going to have to get into some sort of arbitrary law. It goes into a complex thing though, and it's pain in the ass.
Yeah. Finance are just way too complicated. I don't know what your background is with imaginary complex numbers, but you should know that e to the I theta is equal to cosine theta plus I sine theta. I think it's called Euler's equation. You know, Euler. Same Euler as the Euler method we get. So it turns out that instead of this kind of ugly thing, what you get instead is you get y equals some arbitrary constant times e to the minus ax. This is the a from our original equation. Cosine beta plus another constant, e to the minus ax sine beta, where beta is the square root of 4b minus a squared over 2. Oh, let's have the x's again. Okay, so here we have solutions to this quadratic, well, it's not a quadratic, it's a second order linear differential equation. So let's take a look at a real example. Just real examples are usually easier than general problems. So let's say we had the equation, differential equation y prime plus 5 prime plus 4y equals 0, with the starting conditions that y of 0 equals 0 and y prime at 0 equals 1. So we start with e to the rx. Y prime is r e to the rx. My double prime is r squared e to the rx. So we have r squared e to the rx plus 5r e to the rx plus 4 e to the rx equals 0, or r squared plus 5r plus 4 equals 0. Our quadratic formula tells us r equals, the two roots are negative 5 plus or minus the square root of 25 minus 16 over 2, which is negative 5 plus or minus 3 over 2, which is negative 4 or negative 1. So our general solution becomes negative 4x plus another constant e to the minus x. And we're going to need the derivative here. Y prime equals a1r of even r. Negative 4a1 e to the minus 4x plus negative a2 e to the negative x. And since y is 0, which is a1 plus a2 equals 0, and here we get y prime of 0 equals negative 4a1 plus negative a2 equals 1. Well, now we have two equations and two unknowns. See how useful that stuff you learned in high school algebra is? Look this up a little. So in my head, I'm just going to add these two equations, and I'm going to get negative 3a equals 1, a1, so a1 equals negative 1/3. And since a1 plus a2 is 0, a2 has to be equal to 1/3. So my final solution here is negative 1/3 e to the negative 4x plus 1/3 e to the minus x. This, of course, would be a little trickier. My discriminant was negative, and I needed sines and cosines. Okay, that was a lot. Questions about this? Okay. I have a few problems you could try in this vein. I'll give it to you first because I don't want to forget you. Take a stab at these. Anybody else think it's kind of magical? Solve a quadratic equation? Solve a differential equation? I mean, if they told you that in high school, you'll need this to solve differential equations. You go, oh, good. What's a differential equation?
What?
You didn't show up. You're a vampire, right? It's an in-joke. This is what I'm getting here. I just sent it back. Yeah, thanks. Gotcha.
That's cool.
All right, would someone like to do number 1?
I'll do it. The whole thing.
Well, actually, if you think about it, you don't have to do the whole thing. Where is it?
It's the middle section that.
Oh, I erased it. Oh, wait.
That's it's that. It's the board that's hidden there.
This one?
Or that pull the top one down. Never mind, I guess you did erase it. Oh yeah.
Ah, it's half done already. Okay. All you have to do is find the new constants A.
Yeah.
Nobody. Done the whole problem. A1, 0. You add those two together, you get negative 3A1 equals 0.
Well, but why prime of 0 is still 1?
Yeah, but if you add negative 1 and 1, you get 0.
Oh, okay. Yeah, you're right. So, A1 is 0, so then 2.
Yay! Okay, it was easy, right?
Yes.
Would anyone like to try number 2? You just get mad at me if I say, was that a yes?
What? No.
Okay. Someone want to try number 2?
Yeah, whatever, I'm gonna do it on the fly.
I always the same hands. I think you needed a whole new board, so I would decide what. You could use this one over here. It's nice and clean.
So we're going to just whatever we're looking for, copy that down over here, as partial answer.
Well. Huh. Huh. Just do the A part, you know. Don't do the second plug-in. Well, 2 has an A and a B, right? The A is the initial, A and B are initial conditions. So just do the A part.
Well, the problem here is that the determinant is 0.
Uh-huh. So you want to go run over the board over to the right and look at what the answer is?
Oh, so you already did it there. Huh.
Well, I didn't do this problem, I just did the general problem. E to the negative A over 2.
Wait, it's a constant.
It is a constant.
A is 2, right?
Yeah.
A is 2, that's part of the problem.
It was, that A and B is flipped. That's why it's easy.
What?
That A and B is flipped from what you're using. You're using B split.
So we use B where A is, right?
you have, I mean, you have part of the general solution here, right?
Do I need the A1s here?
Yeah. Y is e to the A1. That's all you have to do. That's the solution,
So
right?
A2 here?
Right now, just right there. There's no A2. Right? That's it. That's it, except for the initial condition part of it.
Okay.
You only get one solution.
What's with y prime 0 equals 0?
I don't know. Does that work? I guess that doesn't work, does it?
Yeah.
That doesn't work.
Yes.
So there's no solution with that.
Okay.
Yeah. Okay. All right. So that doesn't work. All right, look, thank you. There's a little bit more here. I know you're all excited. Class is almost over. I don't want you to get too comfortable. I presented a solution to a linear general differential equation. I didn't say that was the only solution. This is kind of an important question in mathematics. You say, well, what's a solution, and then is that the solution? Something interesting happens here. I mean, we only got, using our strategy here, we only got this one solution, e to the minus a over 2x. But what if I looked at the solution that looked like this? Y equals x e to the rx. So the derivative of this is the product rule. And to find the second derivative, I have to do the same thing again. E to the rx plus r squared e to the rx. Now, when I try and add these all together, what do I get? X e to the rx plus r e to the rx plus r squared e to the rx. That's this component. Plus 2 times x e to the rx plus r e to the rx. That's this component. Finally, plus x e to the rx equals 0. Okay, I have to do, I can just eliminate all the rx's, right? Okay, x plus r squared plus 2x plus 2r plus x equals 0. That gives me 4x plus
3r.
3r plus r squared. Better look at my notes. I'm not going to get it right by the end of class. I'll have to
screw around with the columns.
Yeah, I made a mistake, and it's not going to work. But I will say this, strangely enough, we have another solution coming out of left field. So, again, you know, with differential equations, it's not a nice, clean subject like, say, solving an algebraic equation where you always get an equation. Okay, thank you. You may go. Thank you, Kristen.